Hello, everyone. Welcome back. Today, it's a continuation of the topic that we were discussing last week on how do we solve nonlinear problems. And today, to share his approach with us, we have with us Michael Lubasch from Quantinuum. He is the key developer of this technique on quantum nonlinear processing units, and he's going to share with us his pioneering work. And this is a different approach to solving nonlinear problems as opposed to the Cartman linearization approach that we saw last week. And I'm going to introduce Michael. Michael is a researcher at Quantinuum. His work focuses on solving computational fluid dynamics and in general quantum algorithms for other industry applications. And before joining Quantinuum, he completed a postdoctoral fellowship at the University of Oxford, where his work centered on quantum algorithms and tensor network methods for solving nonlinear PDEs. And he holds a PhD in physics from Max Planck Institute of Quantum Optics, where he conducted research with the theory division. And we're very excited to welcome him to this program and to share with us his very exciting work on QNPUs. Over to you, Michael.
Thank you so much for the lovely introduction, and thanks a lot for having me. Okay, so I'll be talking about this work that we've been doing related to solving nonlinear problems with variational quantum algorithms. So before I start with my presentation, I would like to say a few words about our company, Quantinuum, so the company I'm working for, and in particular about our hardware. Let me see if I can move this a bit here. Sure. Not sure where the best place is for this, but this should work. So in particular, with respect to the kind of technological developments that have happened at Quantinuum over the past 5 years. So at the moment, we have a device with 56 qubits. What's special about our hardware is it's based on shuttling ions around. So it's possible for us to work with arbitrary connectivity. So that's very easy for us to do. And then the architecture that we have, it allows us to get really, really accurate 2-qubit gates. And that enabled us to go to these really large values of quantum volume that we can achieve now of, exceeding a number of 8 million. So something like I think it's 2 to the power 23 is what we've recently achieved with our hardware in May of this year. And yeah, I just wanted to highlight that. So let me start with an overview to give you, let me give you an overview of this presentation. So I'll start with a brief motivation before I present a few slides on quantum algorithms for differential equations. So something that is not variational, just to motivate our work on variational quantum algorithms for differential equations. And finally, I will conclude. So to motivate this topic, the motivation is very simple. So our goal is essentially to perform more accurate and more efficient simulations of differential equations. And there are various areas in which differential equations appear. One that I'm sure everyone can relate to is weather forecast. So to predict the weather in the future, one way this is done is by solving these weather equations that have chaotic solutions and nonlinear in general, and they are very difficult to solve. And in particular, the goal here is to go to fine grids, so to take more and more features of the atmosphere into account to get more and more accurate predictions for the weather. And quantum computers might be useful here. Another application area that we looked in ourselves is to use quantum computers to simulate the dynamics of Bose-Einstein condensates as they're described by this nonlinear Gross-Bedajewski equation. Another application that we looked into is fluid dynamics, so to solve the incompressible Navier-Stokes equations as they're written down here, which have numerous applications, for instance, in the context of aerospace companies or defense companies. So So this flow of water around a submarine can be modeled by such Navier-Stokes equations. And you can imagine that there's a lot of industrial interest in solving these equations. Because if you can solve these equations very accurately, you can design these submarines or aeroplanes very well to minimize turbulence around these objects and save fuel, save costs. So it's a very important industrially relevant topic, but also fundamentally from a research point of view, it's really, really interesting. So then another topic that we looked at in the past is this topic of battery simulation, in which, and I'm showing you here a picture of a simplified model of a lithium ion battery, where the process that one's studying here is the process of discharging and charging the battery. And you can imagine if you can simulate such processes, you might be able to model batteries in such a way that they can be charged and discharged more often or faster, right? Which is clearly, again, interesting commercially, for instance, right? Or you might be able to design batteries that last longer or that can be recycled, right? Which is important for the environment. So there's lots of interesting questions one can address here. Another topic that we looked into ourselves is this topic of seismic exploration. In this context, well, one task that can be required is to solve the wave equation essentially. So the idea is to build a model for the underground. So okay, so ultimately the goal, or let's say the goal that I'm talking about here is the goal of discovering oil and gas. So seismic exploration basically is a means to explore and analyze the underground, such as, for instance, the underground below the seabed, where, for instance, oil and gas reservoirs could be located. And then the goal here is to build a theoretical model of the underground um, based on experimental data. And what's done here in this context, for example, is that they have these boats that travel over the ocean, and uh, they perform controlled explosions inside the water that send shock waves towards the underground, such that these shock waves, they get reflected by the seabed and what's inside the seabed, and then these reflections are measured in using microphones, behind this boat. And well, this allows one to get a picture, basically to get some picture in terms of pressure modulations, right, of the underground. And this picture, so this experimental picture that comes from this data, one can try to match a theoretical model for the underground. And by doing that, one iteratively, basically, theoretically models this underground and iteratively adjusts it until it matches the experimental data. One can try to find uh, oil and gas, for instance. Now, another topic that's related to this seismic exploration is this topic of reservoir simulation, in which case the goal is to model an oil reservoir as accurately as possible. And one way to do so is by solving certain nonlinear partial differential equations. The last topic that I wanted to mention here as a motivation is this topic of magnetohydrodynamics, which is also something we worked on at some point in the content. And this topic of magnetohydrodynamics, which I would describe as like a, a very advanced topic in many ways, because it's literally coupling Navier-Stokes equations to Maxwell's equations. It can, for instance, be used to describe what's happening in these fusion reactors. So in this context, what one tries to do is describe the dynamics, so the flow of um, a charged medium, right, a plasma, um, inside magnetic fields, right? So the idea of these fusion reactors is to have a extremely hot plasma And so that's full of charged particles. And to confine those, one needs a strong magnetic field, right? And this can be modeled with these magnetohydrodynamical equations. So all of these problems, they appear in the real world. They have there's a real industrial and commercial interest attached to them. There's also a research interest or an environmental interest, right, attached to the fact that these technologies, they might really improve our lives and help our nature in the future. So I think it's really interesting to think about ways to help solve these corresponding problems more efficiently, right? And quantum computing comes along with new tools, with new means, um, to help us with this. Okay, so let me first spend a few slides on this topic of non-variational, just quantum algorithms for differential equations, just to introduce the overall topic. And in particular, let me talk about amplitude encoding, which is the typical way that differential equations usually are tackled with quantum computers. So amplitude encoding is one way of storing a function on a quantum computer, namely by storing the function values inside the wave function amplitudes of the quantum processor. So a quantum state of L qubits can store 2 to the L function values, right? Just using the 2 to the L complex wave function coefficients of the corresponding qubit register. And what does this mean? So if we have a function in 1D, just as an example, f of x, and we want to discretize that, and our domain of interest goes from 0 to 1, then one thing we can do is we just use an equidistant grid. And if we have a single qubit available, we can store two values in its two computational basis states. And we can, for instance, choose to store these two values, right? So the value of f at x equals 0 and the value of f at x equals 0.5. If we have two qubits available, we can store four function values, and we can, for instance, choose to store these four, which can contain the previous two. If we have three qubits, we can store 8 function values. So you see, as the number of qubits grows linearly, the number of function values we can store grows exponentially. So that's a very nice feature, and is often also referred to as the fact that quantum computers can provide an exponential memory compression, because, well, you just need L qubits to store 2 to the L classical numbers, whereas on a classical computer, you would need 2 to the L, something like 2 to the L numbers, right, to store all these numbers. Something like 2 to the L bits to store all these numbers. So that's like that would be an exact exponential memory advantage, right? But what's nice in the context of differential equations is that your grid spacing decreases by a factor 2 each time. So when you think about solving differential equations, one of the simplest approaches, and perhaps one of the earliest ones that you learn about, is the finite difference method. The finite difference method has an error that's some polynomial of the grid spacing, but as you can see here, the grid spacing always decreases by a factor 2 each time you add a qubit to your state. So you can imagine that this entire approach, that this amplitude encoding is particularly well suited, to work with finite difference method approaches. For instance, because the grid spacing can be made exponentially small just by increasing the number of qubits linearly, right? Okay, so to present some literature. So one thing you've seen on the previous slides is that there's this exponential memory compression with respect to classical resources. Quantum computers can in principle represent the same number of function values, but using just logarithmically many qubits, right? So in terms of grid points, so if you have n grid points, you can imagine that this reduces your cost to something that scales like log of n. Now, while this is somewhat obvious in terms of with respect to memory, so space complexity, with respect to time complexity, that's not as obvious. So we didn't talk about circuit depths yet, right? Which have to do with time complexity. But lots of papers, lots of very clever people have looked into this topic, and they've shown that also in terms of time complexity, in the context of linear differential equations, you can often obtain this exponential advantage. And there's a whole lot of different approaches that one can use here. So one approach is to for instance, if you have the time evolution and you're looking at a linear differential equation that you want to time evolve and you time step that, well, then it turns out you can encode the solution for all time steps into a single system of linear differential equations and then solve that with the HHL algorithm. So that's one approach that Dominic Barry advertised in 2014. Then another approach is in certain cases you can map your linear differential equation to a Schrödinger equation, and then you just need to solve that Schrödinger equation, and that is can be done with techniques for Hamiltonian simulation and can lead to an exponential advantage. But so for linear differential equations, a lot has been done and is known, and in terms of getting a rigorous advantage, this has been shown in many ways. Yeah. The situation is different when it comes to nonlinear partial differential equations. So in this context, I would say until recently, until maybe a few years ago, not much was known. So it turns out that uh, in recent years, really, there have been new insights and new ideas, such as based on, mapping linear problems to nonlinear problems in higher dimensional, mapping nonlinear problems to linear problems in higher dimensional spaces, using mean field ideas, and so on. New ideas have been presented for solving nonlinear differential equations. And in this context, there are also some mathematically rigorous results existent now that prove that quantum computers can offer an exponential advantage under certain conditions in this context too. Yeah. But usually it should be said that the currently existing proposals for nonlinear partial differential equations are not near term. So they either require a large number of copies of the state or complicated circuitry. So it's not near term really, to the best of my knowledge. So that was the motivation for us to look into this problem and look into variational quantum algorithmic approaches. So can I just emphasize at this point, if anybody has a question, please just shout. Yeah, feel free to interrupt me at any point.
Yeah, we did get a few questions. Maybe we can.
Sure, yeah.
Okay. So it's kind of a question on one of your earlier slides. Can the seismic studies with quantum be used for earthquake model study or earthquake predictions?
Can quantum computing be used for earthquake studies?
Yeah.
Um, so I'm sure it can be used in a certain way for earthquake studies. I guess I believe the question is about uh, ultimately, right, whether there can be an advantage of using a quantum computer in this field of earthquake studies. That's a very good question. So I haven't worked on that topic at all. What I want to say is that I think there's a lot of possibilities in which a quantum advantage can be obtained in any context of differential equations. But there's also still a lot of open questions that one needs to address. Yeah.
Okay. Kind of a follow-up on that, maybe has any work been done on combining seismic data with data from quantum gravimeters?
Quantum gravimeters. I don't know. Sorry, I don't know about that.
It's all right. Yeah. Okay. So, can AI be used to develop new types of quantum algorithms?
Oh, absolutely. I mean, so in our company, there's a whole AI department that works on that. So there exist examples where AI has been used in the context of quantum error correction and in the context of compilation, for instance, successfully used, right? So I'm sure there are many ways in which AI can help. Yeah.
Okay. And a few technical questions. How does using a contracted representation like matrix product states of the dense vector affect the algorithm or the results compared to amplitude encoding?
Yeah, that's a very good question. So, I mean, in our work, we are using matrix product states regularly, and we are using them with amplitude encoding. So, what we're doing is we are simply representing the amplitude encoded solution in this tensor network formalism. So, now the problem with that is the tensor networks are limited to low amounts of entanglement. So to be able to work with tensor networks on classical computers, so it should be said that for those who are not familiar with tensor networks or matrix product states, it's a classical representation that is worked with on classical computers, that's efficient on classical computers, and has been used, for instance, to simulate quantum circuits, but also to simulate uh, problems related to differential equations. Um, so the limitations of matrix product states are, in this context of computational fluid dynamics, they are typically limited to low dimensional problems. So they're really good for 1D problems, 2D problems. It's not so clear yet how strong. I think it's fair to say that. I mean, you can use matrix product states for any high dimensional problem. It's just that with a number of variables, entanglement can build up exponentially, just as it happens in standard spectral methods. So so quantum computers are expected to be better than tensor networks or matrix product states in that respect, that they can on a quantum computer, it should be easier to go to high dimensional problems. Yeah, basically. I think that's
Yeah,
basically the bottom line.
yeah, okay, thank you. One last question. What is the lower bound for the computational cost on linear problems using quantum algorithms? Can we achieve strictly less than order of log n?
Can we achieve strictly less than log n? That was the question?
Yeah, that's the question. Or is there a lower bound? That's
Yeah,
the
okay. So there's a lot of details involved when it comes to strict statements. So for instance, when it comes to solving linear differential equations or linear equations like HHL does, right? An important quantity to take into account is the condition number. So there's a prefactor that I'm not talking about here in this simple notation, order n to order log of n. And for instance, and that prefactor depends on the application. It depends on, I mean, the precise details of the problem at hand. So if you're solving a system of linear equations, the key quantity that you have to take into account is kappa, the condition number of the matrix that you're trying to invert effectively. And I think it's strongly believed that the lower bound in terms of kappa is linear in kappa. I think it's kappa log kappa or something like that. So I would have to look that up. But so what I'm showing here is a simplified picture. I don't know if there can be an even lower. So there are certain problems that can be fast forwarded, but that has to do with time evolution. To be clear, I don't know if one can potentially achieve even better complexity than log of n.
Mhm. Yeah, thank you. Yeah, I think I kind of agree with that. I think going lower than log n is probably not possible. All right, yeah, we
Yeah,
can keep going. Thanks, Michael.
thank you. Yeah. So just to give you a quick example for a non-variational quantum algorithm, and one where I would possibly where I think it's probably the simplest non-variation quantum algorithm for differential equations that exists. Maybe you find a simpler one, but this one, I mean, to best of my knowledge, it's the simplest. So it's also one of the first that someone came up with, and and here I will apply it to the 1D to solving the 1D time-dependent Schrödinger equation. And it's very simple, right? The idea is just to use a finite difference method in space, and then to trotterize the evolution to do time evolution, right? To do the evolution in time. And what you see in this very simple example is that the circuit for a single time step is already quite deep. So I wanted to show you this example because it illustrates the fact that even the simplest non-variational approaches lead to deep circuits immediately. Yeah. And how do you see that? Well, take this simple single particle Schrödinger equation and look at the kinetic part. So minus h bar squared over 2m d squared dx squared is the kinetic part, and v of x is some external potential. And to do the time evolution, you want to exponentiate that. And to do the time evolution, you trotterize that. So, and then to obtain gates for the trotterized circuit, um, you well, I mean, you want to have the diagonal operators. So you use the QFT to get these diagonal operators because that's how you define your exponential. And you see that in each time step, you need to use the QFT twice. Now, the standard QFT has a circuit depth that's n squared, so little n squared, or in my notation from before, it's L squared. Um, so you already have 2 times L squared gates here, plus the gates that you need to realize these diagonal operators, right? E to the minus I over h bar dt delta t, e to the minus I over h bar v delta t. And here it really depends on the structure of your problem, how easy you can create these gates. Yeah. So if you have, for instance, a harmonic potential as v of x, it turns out that you can create e to the minus I over h bar v delta t via 2-qubit gates. And similarly for the kinetic energy, if you can assume that your solution is sufficiently smooth with respect to well with respect to the grid you're using, well then you can also create the corresponding diagonal part with 2-qubit gates alone, a product of 2-qubit gates, but those will also scale like n squared. So I mean this example here was just meant to illustrate the challenges that come along with focusing on fully quantum algorithms, non-variational for solving differential equations. Okay, so all of this was just to introduce this topic of variational quantum algorithms. So what did we study in this context? So what we did was, well, we designed these circuits to solve nonlinear partial differential equations. But what did we apply them to, right? So we used different ansatzes, variational circuits, to compare their performance in this context. So one ansatz we studied is the classical matrix product state ansatz. That is, and the reason is that we have a lot of classical matrix product state MPS codes. So it's very easy for us to explore the performance of this MPS ansatz on a classical computer. But then also every MPS can be written as a quantum circuit. And it's been known for a while, and it has this advantage that, so the advantage of knowing that is that it corresponds to a very particular architecture, right? So an MPS is characterized by this parameter chi shown here. And that parameter chi, you can increase it to make your ansatz more expressive. And in this picture that I've drawn here, it corresponds to basically the number of qubits that connect your unitaries here. So if chi is 2, you just have the staircase of 2-qubit unitaries. If chi is 4, you would have a staircase of 3-qubit unitaries. if chi is 8, you'd have a staircase of 4-qubit unitary. So your ansatz gets more and more expressive as you increase chi. So that's one ansatz we studied. And we compared the performance of this ansatz, which for small values of chi can be handled very easily on classical computers, to the performance of a brickwork circuit, in which case one has this alternating layered ansatz, and the circuit depth is the parameter that one can change to increase or decrease the expressivity of the ansatz. Right, and this circuit is strongly believed to be, in general, hard for classical computers, but feasible for quantum computers. And then we developed basically a VQE algorithm for the nonlinear Schrödinger equation to illustrate our ideas. And in this VQE algorithm, what we did is we took the nonlinear Schrödinger equation, so that's also known as the Gross-Bedayevsky equation. We looked at it in 1D, and we used the finite difference method to obtain matrices and vectors describing that problem. And our goal was to compute the ground state of that Gross-Bedayevsky equation. And you can do that by defining a certain cost function C. That's a sum of 3 terms in this particular case. The first K being the kinetic energy that takes on this form, where H is the grid spacing. The second term is the potential energy, which takes on this form, and the third term is the nonlinear part, the interaction energy. And if you minimize this cost function with respect to your variational parameters, you'll get a ground state approximation. So depending on the expressivity of your ansatz, that approximation will be good or bad. Now, at the time when we worked on this, it wasn't really clear how to compute these quantities, in particular the nonlinear psi k to the power 4 sum, efficiently on a quantum computer. And that led us to propose what we refer to as this quantum nonlinear processing unit. So it turns out that it's quite straightforward to compute these nonlinear terms as well. What you do is effectively use copies of your state, but it's a small number of copies that's independent of, for instance, the integration time or whatever else defines your differential equations. The number of copies is fully determined only by the degree of the nonlinearity in your differential equation. And then the QNPU, it's drawn here as a black box, but so it takes on a specific form depending on which term of your Hamiltonian you want to evaluate. And I'll show you a few circuits in a moment. So what it does is, so this circuit, what it does, and you can see it's like a Hadamard test-like circuit. It allows you to evaluate essentially any finite degree polynomial of your function. Yeah, basically that's it. Right, where your function is encoded in a circuit, right? In a parameterized circuit represented by some u of lambda acting on 0. Okay, and just to give you an idea for how these circuits can look like, so for the kinetic energy, we want to realize this shift operator to give us this overlap between psi k plus 1 and psi k, which is required for calculating this k expectation value. And it turns out that the circuit based on Toffoli's and using a few Anschiller qubits does precisely that job. Then for the potential term, what you can do is use a circuit of this type. So I have to emphasize that there's many other ways in which one can compute the potential term, but also the kinetic term, right? It's just that in this QNPU picture, that's one way of doing it. So you would encode the potential in this unitary V acting on zero, and then you would again have a circuit of this type to fit in this QNPU picture, right? And one way of obtaining this V unitary acting on zero, which represents your potential function, is in fact to use a matrix product state, so a classical representation, and then because that can be prepared and worked with very efficiently classically. So for some V functions, that will be appropriate and accurate enough. And then one can turn an MPS always in a straightforward way into a quantum circuit. So, and finally, the nonlinear part, which requires copies of the state, can be computed with this QNPU Hadamard test-like circuit in this way. So, and having developed these tools, we then try to find an example, a problem where we could see an advantage of using this brickwork circuit that I showed at the beginning of this section over this MPS ansatz, which is classically very efficient, right? And so we looked at the ground states of this Gross-Podayevsky equation in 1D using an external potential V of x of this type, which is the sum of two signs, right? Which have these two weights S1 and S2, and which have two wave numbers kappa 1 and kappa 2 that we've chosen in this golden ratio way, such that the waves are incommensurate. So one gets a lattice. So this V of x is quasi-random. So by choosing these kappa 1 and kappa 2 in an irrational ratio, one gets a lattice that if S1 is approximately as large as S2, that looks quasi-random. So if you study ground states, if you look at ground states at this lattice, you'll see these two types of ground states, right? So if either S1 or S2 is really large, then you can, in that case, you can just neglect the other term, and your potential is effectively just one sign. And it turns out that your ground state just replicates that sign structure. So that's the green solution here. So in this figure, I'm just showing you two ground states for two different configurations, considering 8,192 grid points and certain values of these wave numbers and the interaction strength. And you see, if S1 is much larger than S2, you just get this very smooth, very regular sign structure. But if S1 is of the same size as S2, right? If S1 divided by S2 is 2, you get these, you see very exponentially localized peaks. And that's basically a reflection of the quasi-random external potential. So you see this quasi-random external potential has minima in quasi-random places, and in these minimas, your wave function will localize, right? And that's what the blue peaks are about. And you can also see they're exponentially localized, right? And you can then address the question, how easy is it to represent these functions using the MPS ansatz and the quantum circuit ansatz? And you'll find the MPS ansatz does really well representing the green function, so which is very structured, right? It's just a single sign function in principle with a little bit of perturbation around it. But it's much harder for the MPS function to capture something like, for the MPS ansatz to capture something like these blue peaks. And that is precisely the scenario that is exactly where the quantum circuit outperforms over MPS significantly. So that's basically what we saw in our analysis, that this brickwork circuit is much better suited. And for what we've seen numerically, it's exponentially better suited to represent these quasi-random functions, yeah, when compared to MPS. And this brings me to my conclusions. Okay, but before I come to my conclusions, I would just briefly like to use this chance to advertise like our latest paper that followed up from this previous work, in which we studied how time-dependent nonlinear partial differential equations can be solved in a ground state procedure, so in a VQE way, for all time steps, basically using the QNPU formalism. So that's what this paper is about. And what we've also done in this paper, so the idea is to encode the solution to your differential equation for all time steps in the ground state of a certain Hamiltonian. And it turns out historically, this Hamiltonian has also been referred to as the Feynman-Kitaev Hamiltonian. So essentially what you do is you treat your time dimension like a space dimension, right? So if you have a one dimension in space and one dimension in time, you can equally look at this problem as a two-dimensional problem, right? One plus one dimension. But what you need to do to solve the problem is somehow in this way, in this VQE way, is you need to encode the solution in the ground state of a certain Hamiltonian. And it turns out that one can do this efficiently, and we've investigated this so-called Feynman-Kitaev formalism in this paper here. And we've also run experiments where you can see really nice 1D solutions to the Burgers equation here in figure 3a, b, comparing well, this asymmetric evolution that you get in Burgers equation in 1D and running it on our hardware, that's A, and on IBM hardware, B. And similarly, we see if we look at just the diffusion equation starting from a sine function, what's shown in figure 3, C and D, right? There's also an alternative approach that I'd like to highlight. So when using quantum computers, there's a lot of things you can do, and a completely different approach to ours to solving nonlinear partial differential equations with variational circuits. It's this approach here based on differentiable, so-called differentiable quantum circuits. So this is a completely different approach that does not use amplitude encoding, and therefore, I mean, it's slightly harder, or it's a bit different when it comes to addressing the question of quantum advantage. So when you use amplitude encoding, the advantage is that you can immediately argue there's an exponential advantage in memory. When you don't use amplitude encoding, you can end up with easier operators, right? Easier ways to treat boundary conditions. And that's, for instance, what's happening here in this differentiable quantum circuit approach. But perhaps it's maybe a bit more difficult in general to show and argue for a genuine quantum advantage. Yeah. But I guess in this field of variation quantum algorithms, it's generally hard to argue for a rigorous quantum advantage. I think that's important to say. Okay, so to conclude, I've presented a few slides on quantum algorithms, non-variational algorithms for differential equations. I think the beauty of these non-variational approaches is that there have been many different studies now. There have been many different techniques used. There are many different approaches out there, and they all show, some sort of exponential advantage in some regime under certain assumptions, right? They have mathematically rigorous performance guarantees, so that's also very nice. But the challenge with non-variational approaches is still that they require advanced quantum hardware. On the other hand, variational quantum algorithms, they can also provide, under certain assumptions, looked at it in a certain way, an exponential quantum advantage, right? And that's something we've seen in numerical experiments for a certain problem by comparing to matrix product states. So the problem that I think is an important one in the context of variational quantum algorithms is the lack of rigorous performance guarantees. Um, there's still a lot of open questions related to many aspects of variation quantum algorithms. But the beauty in this context of the beauty is that one can run them on current quantum hardware, right? And with this, I thank you for your attention.
Thanks, Michael. That was awesome. I thought it was such a difficult topic, but you presented it so clearly and concisely. Thank you for that.
Thank you.
Yeah, we have a few questions coming on Discord that I'm going to read out to you. So in your slide on the Schrodinger's equation, when you increase the trotter depth for the 1D problem, what kind of setbacks or diminishing returns do you observe? And does that depend on V of X?
Yeah, so if you increase the circuit depth in your ansatz, you encounter several problems. One is one is related to this problem of barren plateaus. So the question, how do you train a deep circuit? So how do you avoid exponentially vanishing gradients in a deep brickwork circuit? Because you know that that happens if you randomly initialize your circuit. So one problem that appears with as you increase your circuit depth, your training gets harder, and you have to choose a clever way of training a deeper circuit. And then besides that, uh, clearly a deeper circuit requires more time to run on hardware. It also accumulates more error, right? So gates have errors, so that's another downside. How does it depend on V? So the ansatz itself can be chosen independently of V, as I guess it's as always in these variational quantum algorithms. But clearly, if your goal is to say for a certain accuracy epsilon, how do I need to choose my circuit depth? How does that depend on V? Well, that clearly depends on V in some way, and you could require if you change your V to something that gets like completely random without any structure, you can imagine, requiring exponentially deep circuits simply because there's no way that your ansatz can solve that problem without exponential depth. Yeah, does that answer the question?
I think so. If there are any more follow-up questions on that, I will let you know. We can take a few more questions. Are there optimization techniques for reducing the circuit depth for a shift operation on a set of qubits? And is the shift always just by one?
Uh, are there techniques to reduce the circuit depth of the shift operation? So the best way that I know of to realize the shift operation is to use the quantum Fourier transform. Yeah, that's just how it is. If you go to Fourier space with a quantum Fourier transform, your shift operation gets really simple and your circuit gets really simple. Um, sorry, what was the second part of the question?
Is the shift always just by one?
Yeah, the shift could be, I mean, it's a good question. It could be by more than one. So in my experience, the shift operation has always been by one. I don't know. I don't know any applications. I guess you could think of um, higher order finite difference representations of differential operators that require larger shifts. So yeah, it's a very good question. I guess you could shift. You could go to higher orders by applying the shift operator several times, right? But yeah, I mean, it's a very good question. I haven't worked with higher shifts. Yeah.
Okay. I guess like maybe a broad general question, for if people want to use your approach to solve their own nonlinear problem, where do you suggest that they start? How do they start thinking about constructing the QNPUs?
That's a very good question. I would say the easiest way to start is to look at the one-dimensional Schrödinger equation, and to try to understand how the formalism works without the nonlinearity. I would say that is the easiest way to start. Um, and only afterwards add the nonlinear part to that. Um, I guess it depends a bit on the problem of interest and what kind of equation they want to tackle. So for the time independent problems, I would say this approach, I would recommend to look at this paper and look at this approach in that paper and try to adapt what you're doing accordingly. But for time-dependent problems, I think it makes sense to look at this paper and try to find out how can you phrase your problem in that way. And in this paper, I mean, we present the formalism for the diffusion equation and Burger's equation. I think it should be understandable, right? Or alternatively, just send me an email, right? Yeah.
Yeah, thank you. Yeah, thank you, Michael. That was awesome. Thank you once again for taking the time to share your knowledge and insights on this problem with us. We really appreciate it. I certainly learned a lot, and we already have comments coming in on Discord thanking you for this amazing lecture. Yeah, thank you once again.
No, thank you. Thanks a lot for reaching out, and it was a pleasure. If anybody has any questions, please just send me an email. Yeah. Thank you.
Yeah, thank you.